Self-assembling 3D battery would charge in seconds. By Tom Fleischman. The world is a big place, but it's gotten smaller with the advent of technologies that put people from across the globe in the palm of one's hand. And as the world has shrunk, it has also demanded that things happen ever faster, including the time it takes to charge an electronic device. A cross-campus collaboration led by Ulrich Wiesner of the Spencer T. Olin Professor of Engineering in the Department of Materials Science and Engineering, addresses this demand with a novel energy storage device architecture that has the potential for lightning-quick charges. The group's idea, instead of having the battery's anode and cathode on either side of a non-conducting separator, intertwine the components in a self-assembling, 3D gyroidal structure, with thousands of nanoscale pores filled with the components necessary for energy storage and delivery. This is truly a revolutionary battery architecture, said Wiesner, whose group's paper, Block copolymer-derived 3D interpenetrating multifunctional gyroidal nanohybrid for electrical energy storage, was published May 16 in Energy and Environmental Science, a publication of the Royal Society of Chemistry. This three-dimensional architecture basically eliminates all losses from dead volume in your device, Wiesner said. More importantly, shrinking the dimensions of these interpenetrated domains down to the nanoscale, as we did, gives you orders of magnitude higher power density. In other words, you can access the energy in much shorter times than what's usually done with conventional battery architectures. How fast is that? Wiesner said that, due to the dimensions of the battery's elements being shrunk down to the nanoscale, by the time you put your cable into the socket, in seconds, perhaps even faster, the battery would be charged. The architecture for this concept is based on block copolymer self-assembly, which the Wiesner Group has employed for years in other devices, including a gyroidal solar cell and a gyroidal superconductor. Joe Ergwerner, Ph.D., 15, lead author on this work, had experimented with self-assembling filtration membranes, and wondered if the same principles could be applied to carbon materials for energy storage. The gyroidal thin films of carbon, the battery's anode, generated by block copolymer self-assembly, featured thousands of periodic pores on the order of 40 nanometers wide. These pores were then coated with a 10 nanometer thick, electronically insulating but ion-conducting separator through electropolymerization, which by the very nature of the process produce a pinhole-free separation layer. That's vital, since defects like holes in the separator are what can lead to catastrophic failure, giving rise to fires in mobile devices such as cell phones and laptops. The next step is the addition of the cathode material, in this case sulfur, in an amount that doesn't quite fill the remainder of the pores. Since sulfur can accept electrons but doesn't conduct electricity, the final step is backfilling with an electronically conducting polymer, known as PEDOT, poly-3,4-ethylene deoxythiophene. While this architecture offers proof of concept, Wiesner said, it's not without challenges. Volume changes during discharging and charging the battery gradually degrade the PEDOT charge collector, which doesn't experience the volume expansion that sulfur does. When the sulfur expands, Wiesner said, you have these little bits of polymer that get ripped apart, and then it doesn't reconnect when it shrinks again. This means there are pieces of the 3D battery that you then cannot access. The group is still perfecting the technique, but applied for patent protection on the proof of concept work. Other collaborators on this work included Ettore Brugner, the Emil M. Chamot Professor in the Department of Chemistry and Chemical Biology, and Gigi Rodriguez Calero, Ph.D., 14, formerly of the Brugner Group. This work was supported as part of the Energy Materials Center at Cornell, EMC2, funded by the U.S. Department of Energy as well as in part by the National Science Foundation. Experimentation was conducted at the Cornell Center for Materials Research, CCMR, and the Cornell High Energy Synchrotron Source CHESS, both of which are supported by the NSF.